got to do this cinch term, but don't worry, it's a cinch. You're right. I have to write it on both, or I owe you parentheses. Thank you. Oh, thank you. Yeah, that was a very, I think if I just took a step back and looked at that for a second, I would have been like, what? Thank you. Yeah, cinch. Because it's the difference. Very good, very good. Thank you. So I'm glad I can make these mistakes for your learning. Let's see here. 3v, all on purpose as usual. Let's see here. 1/4 e to the 2v minus e to the minus 2v e to the 3v minus e to the minus 3v. FOIL this thing out. E to the 5v minus e to the minus v minus e to the v plus e to the minus 5v. Hey, now we got some coshs. So this is 1/2 cosh 5v minus 1/2 cosh v. I was putting that up. That we're integrating over v though. So. Okay, glad to help. Let's see here. 1/2 cosh 5v minus 1/2 cosh v. I hope your maybe your problem's not quite this awful, eh? Didn't I have plus 1/2? Oh, yes, I see what you're saying. All right, have we found all my demons yet? Let's see here. Okay. Now we integrate. We're done. So that gives me 1/10 cosh of 5v plus 1/2 t rather plus 1/2 cosh, an idiot, cosh of t. But then we subtract the lower bound. Don't ignore it. It's there. What's cosh of 0? What's cosh of 0? It's 1. So I get a half. Why did I? Oh, integrating. I get 1/10 plus 1/2, which is what? 6/10. Yeah, 3/5. So minus 3/5 from the lower integration. Minus 1/6 cosh 2t. And this gives me what? 1/10 sinh of 5v t rather minus 1/2 sinh v. This time sinh t rather. This time, of course, the lower bound doesn't give us anything because cinches are 0. Sinh of 0 is 0. And there you go. And to quote Dr. Wang, it is somewhat ironical. Oh, no, it's not. But I do think this simplifies. I do. I'm quite certain this simplifies. There's something nice going on here. Like what happens with this cosh cinch thing. It's cosh 2t, cosh 5, sinh 2t, cosh 5t. And we can rewrite that as like what? 1/60th, right? And we got ourselves a sinh 2t, cosh 5t, right? And then what's the other thing over here? Minus what? sinh 5t cos 2t, yeah, or however you want to write that. These are both. What's 3? It's minus. What's that? What do you say? Yeah, something like that. I'm going to stop here. I think we've done enough. My eyes are starting to get blurry on this. I'm not going to do anything more. It's enough. I do think we could clean it up, but I'm going to stop there. Despite I'm fighting clarifying that further, but I think that's quite enough. The point is, you have to write down this integral and then do it. Yeah. Which can be challenging. Yeah. Yes, sir.
Our algebra was totally off and we totally botched the integrating stuff.
Yeah, like at least 10% credit, yeah. What? Oh, for the problem, yeah.
So you want to
Well, if it's a problem about convolution, I think that's kind of a question about integration, at least a little bit. I don't know. At least setting up the integration correctly is worth something, right? Getting to this step correctly is worth more than 10%. I'm joking, of course, but yeah. Okay. I should start talking to you about something else for a little bit here today. So let's spend the last, 8 minutes about something called energy analysis. Well, we won't get to energy analysis. Let's just talk about phase plane analysis. Or the phase plane equation, as it's sometimes called. So suppose what we're dealing with here is a system of two ODEs, so-called autonomous. And so what that looks like is basically we've got dx dt equals to some function of x and y. We've got dy dt equals to some function of x and y, right? But the reason it's autonomous is that the time dependence does not appear on the right-hand side here. All of the time dependence of the differential equation itself is wrapped up into dx dt and dy dt, all right? This kind of system of different, and I'm not saying that f of xy and g of xy are linear, right? If f of xy and g of xy happen to be linear combinations of x and y, we own that problem already. Fine, it's an eigenvector problem. We find the eigenvectors, find the eigenvalues, put our solution together, right? But what I'm about to describe to you works in the context that we can't solve these equations, and it gives us sort of qualitative methods to understand these sorts of systems. So one of the first things you try to do here is to eliminate time and see if you can just sort of go old school on it, so to speak. And by old school, I mean calculus 1 or 2. So to eliminate time, what do? How do you eliminate time from this problem? But that begs the question of how you solve it, right? Divide them by each other. I like that. So what happens if we take dy dt and we divide by dx dt? What should that be? You want to say dy dx, don't you? And guess what? You'd be right. So that would be equal to, now what's the context that you're right? So if you have, if we have, well, it goes back to the study of parametric calculus, right? If you have a parameterization and you look at if you look at the ratio of the y velocity and the x velocity, that gives you the slope of the parametric curve at that point, right? This is like somewhere in Calc 2 we do this, right? But there you go. This is the so-called so-called phase plane equation sometimes. I mean, I don't know. This is what Nagelsaff and Snyder calls it, I think. I'm not sure what's a good name for it, but I'll put some quotes on this because I'm not overly fond of this terminology. But it's a really neat trick. Very possibly. Thank you. Yeah, I can't do math. All right. Thank you. See, but isn't that great? Common sense led you to that. I mean, it's a very natural thing to think of, isn't it? So, for example, one of my favorite systems of differential equations that we could solve by the methods we already know is this, right? Dx dt equals to minus y and dy dt. It's like my go-to example for something that's interesting but not too hard, right? We solved this with Laplace transforms at the end of last class. It was easy, right? So what's the phase plane equation for this example? So we got what? X over minus y, right? So we can separate and integrate, right? So this, of course, gives us x squared plus y squared equals to r squared. So it doesn't give you a solution to the original differential equation, right? But it gives you level curves, which if you found the right kind of parameterization of the level curve, that would be a solution to your differential equation. So it's almost as good as actually solving the original differential equation, but it's disorienting, right? After you divide the t, you lose all sense of, is it clockwise, is it counterclockwise, right? Because if you look at it, this and this both give you the same phase equation, but one of these is clockwise and one of these is counterclockwise. Solution set, yeah? Both circles, though. Where this gets really interesting is in its application to physics. In particular, you can look at Newton's equation for a conservative force, right? So what's that? That's what? Y prime prime, my prime prime equals to what? Conservative force, what is it? Minus d, goodness gracious, minus d, I'm an idiot. Good grief, the force, right? Conservative. And that would be what? That would be equal to minus d, the potential energy, whatever you want, let's say u, right? dy in this notation. One-dimensional problem. And so if let's just say m equals to 1 to keep things easy, then we've got what? We've got, if we let y equal to x1, right? And, well, let's just keep y. I'm sorry, I'm an idiot. Keep y. But let's let v equal to y prime, right? Then what do we have? V prime is what? Minus du dy, right? Which is, by the way, just the force. The force is, in fact, just a function of y, right? It's a conservative force. It's not a function of time, right? So when you look at the system of equations we have here, what we got is we've got dy dt equals to v, and we've got dv dt equals to the force as a function of y, right? So this, much like star, is an autonomous system of ODEs. And you can eliminate time by dividing them, right? So you divide these, this gives us what? This gives us the equation dv dy equals to what?
F of y.
Mm-hmm. Separate, integrate, v dv equals to f of y dy. we have 1/2 v squared is equal to work done by F. Maybe we'll talk about this more, but basically there's conservation of energy right there. Or it was the work energy theorem anyway. So you can play this game to study solutions to Newton's equations, but I don't have enough time to do it justice today, so I'll shut up. Thanks, guys.